Okay. So yeah, exams, I'll get those back to you Friday. I'm not quite done grading them yet. Anybody have any homework questions? I don't think I gave any homework after the test. Okay, so we're going to finish the last part of particle kinematics. And that is rolling without slipping. You can have things that roll that are not round. Watermelons can roll, you know. But what I'm going to tell you here only works for things with a round cross section. Okay. Let's say a circular cross section. So what I'm going to tell you works for, it would work for a pipe rolling down a hill or a ball or whatever, anything where if you take the side view perpendicular to the direction it's rolling, what you see is a circle. Okay, you with me on that? So an oblong thing like looping down, that you have to use different math for that. So the first, so how do you derive this equation? I'm not going to go through the derivation. I used to, and I used to make people remember it, but it just seemed like it took too much brain space away from other stuff. So, so I'm just going to sort of talk about where this comes from. What does it mean? So what does without slipping mean, mathematically, kind of? How are we going to define without slipping in physics terms? We're going to think of it as two requirements. So first, and both of these, I guess, are at every instant. First, the point in contact with the surface think about what it would mean for something to be sliding. The point that's in contact with the surface, think about the velocities of the surface and the velocity of that point that's in contact. One way that it can be sliding is if the point in contact has a different velocity parallel to the surface than the surface does, right? You can think of that as, if you had to define sliding, maybe that's what you would come up with. Are you with me on that? So the point that's in contact with the surface has, I don't need a comma there, has zero velocity parallel to the surface. That's a nice, simple way to write it. I do want you to notice that if in your coordinate system the surface has a velocity, then it's really just that those parallel velocities have to match each other, But, and then there's one other one that maybe you wouldn't think of instantly, but it makes perfect sense. The same thing with acceleration. So even if the velocity is 0 parallel to the surface, you can't have a different acceleration than the surface parallel to it. You know, that's just the start of sliding, kind of. Okay, so the point in contact with the surface has 0 acceleration parallel to the surface. And with those two requirements, so to derive the rolling without slipping equations, you just combine these requirements, these two requirements, with relative motion. And so you can always think of the acceleration of any point on a wheel or a disc, whatever that's rolling along a surface. You can do that calculation as the acceleration or velocity of the center of the wheel plus the acceleration of the point on the wheel relative to the center. It's a relative motion thing. Okay, so I'll write it as so the velocity of the point relative to the ground is equal to the velocity of the point relative to the center plus the velocity of the center relative to the ground. Same with acceleration. So the acceleration of the point relative to the ground is equal to the acceleration of the point relative to the center plus the acceleration of the center relative to the ground. And these two are circular motion. Okay, so, and I'm just going to call these two the velocity and acceleration of the center. You know, like I always do, if I just ask you for a velocity or an acceleration of a point, I'm assuming that the ground is the reference. So this is the velocity of the center and the acceleration of the center. And so using these, here are the two equations. So if you always use a coordinate system that's aligned with the surface, and so this is the center of the thing. Our coordinate system is always going to have the y-axis pointing out of the surface and the x-axis along the surface. Notice that's the same coordinate system you used in Physics 1 for friction and sliding, rolling things. This direction counterclockwise is a positive value of angular velocity and a positive value of angular acceleration. That's the way we've been defining those always. Then the velocity of the center is equal to negative omega r 0, 0. And the acceleration of the center is negative alpha r 0, 0. So this really is all you have to remember to know how to use this stuff. This is all just a little bit of background about where it came from. Okay, so let's do an example.
If it's not in that coordinate system, would we use rotation matrix?
Yeah, exactly. Yes, that's exactly what you would do. So notice that this is a planar motion. So the omega and alpha would never change because those are z vectors. And so all you would do is you would calculate the stuff like this, and then you would use a rotation matrix to re-express it in the coordinate system you want. Yeah. Okay, so let's do a calculation. So let's say we have an object rolling along a surface like this. And let's say it's going, it has an angular velocity this way of 4 radians per second, and an angular acceleration also this way of 6 radians per second squared. And the radius of this thing, I'll just draw it in here, is 0.2 meters. And let's figure out the acceleration, velocity and acceleration at the center. And then let's calculate the velocity and acceleration at the contact point. And then the velocity and acceleration at the top, exactly opposite the contact point. All right, everyone with me on that? So for the first one, we're definitely using a coordinate system like this. And we're just going to use the 2 formulas we have here. So for the velocity at the center, given the direction of that rotation, so we know that this is going to be, the velocity is going to be negative omega r 0, 0. Given the direction of the angular velocity, is omega positive or negative?
Positive.
Well, so that's a clockwise rotation, and so omega is negative.
Yeah.
And then you put it in there, and so we have negative of negative 4. R is 0.200. And so you get positive 0.800 in meters per second. So in other words, the center of this thing is moving down the ramp this way at 0.8 meters per second. Any questions about that? Okay, the acceleration of the center is negative alpha r 0, 0. Again, alpha is negative here because it's clockwise. So this is negative of negative 6 times 0.200. And so you get positive 1.200. And again, that's just down the ramp at 1.2 meters per second squared. Any questions about that? Yeah.
What's the reason for thinking about it as like a separate formula from our WR and AR WR and just ignore the second half of the acceleration?
Well, it turns out to sort of look like that, but that's not exactly why it is. Like, if you go through the derivation, it's not quite that simple, but it does end up looking like that. I mean, so whatever you want to remember, just to remember it is fine, but the derivation goes a little different than that. Yeah. Any other questions? Okay, so this is just using the formulas, and that's what it says, and it makes sense. If you look at the direction of the angular velocity and angular acceleration, you would expect those to be down the ramp, right? Or you'd expect them to be that direction along the surface. So now let's figure out what's going on with that point A. And for this one, and for the point B, we're going to have to use relative motion for this, okay? So relative motion says the velocity of A relative to the ground is equal to the velocity of A relative to the center plus the velocity of the center relative to the ground. And this we just calculated. And this one, so the velocity of A relative to the center is like imagining that the center isn't moving and just calculating the circular motion of that point A around the center. Okay? Do you see that? Like relative, when you're calculating anything relative to the other thing, you can imagine that what you're calculating relative to the second subscript, that thing is just fixed, and you're seeing what the thing is doing around that. Okay. So this, we're just going to use our equation for velocity in circular motion that says omega cross r. So the velocity of A relative to the center is, what's our omega as a vector? It's -4, and in what component? Z, right. So this is 0, 0, -4. And now we have to think about our R vector. What is the R vector, what point does the R vector go from, and what does it go to?
Center to A.
Center to A, perfect. And so this is in our negative y direction. See that? And so it's going to be 0, -0.20. And so you get -0.800. And so now put those together, the velocity of A relative to the ground is equal to negative 0.800 plus the velocity of the center that we already figured out is positive 0.800. Add those up, and you get that at that instant, the point in contact with the ground is at rest instantaneously. You might think at first, like, that was an assumption I made because I talked about how these equations are derived. And I said, like, okay, we're going to start by assuming something about the velocity of that point being the same as the velocity of the ground, of the surface. But notice that the assumption we made only said one component is 0. Okay, it didn't say anything about the other. I mean, this is all happening in a plane, but it didn't say anything about the y velocity. But this says that not only the x component, but the y component are 0 at that instant. Okay. And actually, if you take a picture with with like sort of the right amount of exposure time, you know, the right shutter speed of like a spoked wheel going around, you'll see every spoke in your photo will be blurry except that one down at the one pointing down, which will be perfectly clear right down at the bottom of the spoke and get blurrier as you go up towards the top. So yeah, that point is instantaneously at rest. Okay, now what about the acceleration? I mean, if you had to guess the acceleration of this point A, you'd probably guess 0. It's not going to be the case, though. So we're going to do it the same way. The acceleration of A relative to the ground is equal to the acceleration of A relative to the center plus the acceleration of the center relative to the ground. This one we just calculated in part A. And this one, again, that's circular motion, assuming that the center is fixed. So this is the watermelon equation. All ripe watermelons will rot.
I'm overthinking this. You're saying that the center's fixed, but technically the whole thing is moving. So
That's just what, like, you can think of whenever you're doing relative motion, okay? If the second subscript in your relative motion, you can always think of that thing as fixed, okay? Like when you're calculating that particular piece of the relative motion. Or maybe a more accurate way to think of it is the camera that you're using for measurements is moving exactly with that second subscript, okay? So in this case, we're taking this measurement that we're going to take here, the acceleration of A relative to C, we're taking that with a camera that's moving exactly with the center, okay? So that camera doesn't see the center's motion. All it sees is what the other points are doing relative to the center. Okay, so the acceleration of A relative to C is equal to, our alpha is 0, 0, negative 6. Our r vector is the same as it was for the velocity, so that's 0, negative 0.20. Our omega is 0, 0, negative 4. The r vector is 0, negative 0.20. And so for this one, you get negative 1.200. For this first piece, you get negative 0.800. And so for this whole thing together, you get positive 4.80. And so the total acceleration of A relative to C is negative 1.2, positive 4.80. Now put them together to get the total. So the acceleration of A relative to the ground is equal to negative 1.2, 4.80, plus the acceleration of the center, which was 1.200, and you get 4.80.
I think it should be 3.2 instead of 4.8. 0.8 times 4.
Point. Yeah, 0.8. Yes. Thank you. I was looking at the 1.2. 3.2. Thank you. Okay, so the velocity of that point in contact with the surface is 0. It's instantaneously at rest. The acceleration is not 0. Horizontally, parallel to the surface, there's no acceleration, but it does have acceleration perpendicular, which represents the centripetal acceleration. Okay. So this has no acceleration parallel to the surface. But there is centripetal acceleration. Why don't you take a couple of minutes and see if you can work through the calculation for the vector calculation for the acceleration at that point B, okay? And then I'll go through it and make sure that you're thinking about it the right way. So first I'll do the velocity. So the velocity of B relative to the ground is equal to the velocity of B relative to the center plus the velocity of the center relative to the ground. Center relative to the ground is what we know. Circular motion gives us the velocity of B relative to the center. So this is 0, 0, negative 4. And what's the r vector for the point B?
From C to B.
From C to B. So this time it's going to be 0, positive 0.20. And so that is positive 0.800. And so now put these together, and you get that the velocity of B relative to the ground is equal to 0.800 plus the other one was 0.800, and you get 1.600 meters per second. So the top is always moving twice as fast as the center relative to the surface if the surface is moving. Any questions about that? And now the acceleration. The acceleration of B relative to the ground is equal to the acceleration of B relative to the center plus the acceleration of the center relative to the ground. The acceleration of B relative to the center. This is the watermelon equation. So we have 0, 0, -6 crossed with, it's the same R again, so 0.20 plus 0, 0, -4 crossed with the quantity 0, 0, -4 cross 0.20. So this one ends up being 1.200. This one is positive 0.800. And then these together come out to be 0, positive negative 3.20. And so all together these come out to be 1.2, negative 3.20. And now put it into the relative motion. The acceleration of B relative to the ground is equal to 1.2, negative 3.20 plus 1.200. So 2.4, negative 3.20. Any questions about that? Okay, so there's not much else that can happen with rolling problems. This is just pretty much it. Just remember to always use a coordinate system that's aligned with the surface. Okay, we'll get back into this when we start doing kinetics, and we'll be able to like calculate accelerations due to gravity down ramps and stuff like that. Okay, so now we're going to get into the next topic, particle kinetics. And particle kinetics are governed by a single equation of motion. One vector equation of motion. And that's Newton's second law. It's a real good law. Way better than the stupid first law. And I'm just always going to abbreviate this N2L because I'm going to write it a lot. Newton's second law. And Newton's second law says, add up all the forces on a body. And those are vectors. So F net, it's the sum of all the forces, is equal to the mass of the body times the acceleration. But, well, we were just seeing with rolling, very clearly with rolling without slipping, different points on a body have different accelerations in general. So we got to be really careful about what point we're choosing on a body for this equation. This is true for some choice of acceleration and not true for the acceleration of some other point. So what's the point on the body? Center of mass, yep. And so not necessarily the geometric center, but center of mass. Are we in this class? Yeah, we are going to have to, yeah. Okay, so there is the equation of motion. And let me write this stuff down. So F net is the sum of all the forces on the chosen body. M is the mass of the chosen body. ACOM is the acceleration of the chosen body's center of mass. And one thing that you have to always keep in mind when you're using this is Newton's second law only holds for an inertial coordinate system. And the requirements of an inertial coordinate system are that the origin is not accelerating. And 2, that the axes aren't rotating. By rotating, I mean changing orientation over time. Okay, let's think about why this is for a second. So why can't the origin be accelerating? Let's think about somebody in an elevator, and let's say that they're standing on a scale that's like our force sensor. And let's say that this elevator is accelerating up. And our coordinate system is a camera that's fixed in the elevator that's measuring the person's motion. Okay, so this camera is our coordinate system. Well, this camera let's do it the other way, because this, I think it's a little more intuitive actually now that I think about it. So let's say that this is accelerating down. Let's say this is a little more morbid, but let's say this elevator's in free fall. But let's say there's a lot of pillows at the bottom, he'll be fine. Okay, so this person is accelerating. The coordinate system origin is also accelerating because it's fixed to the elevator. Okay, so what does the camera see? So according to the coordinate system, what's the person's acceleration? You know, well,
Zero.
right. I mean, the camera just sees this guy standing there getting increasingly terrified. You know what I mean? So, like, according to this, there's no velocity and no acceleration. But we know that the net force on the person is mg down. Okay? So Newton's second law doesn't appear to hold in this coordinate system. Are you with me on that? Now let's think about why the coordinate axes can't be accelerating. Rotating, I'm sorry. Why can't the axes be rotating? So let's imagine this setup like they always have in comedy movies about astronauts. This like training thing, I think they call it a centrifuge. So,
Oh, you mean the vomit comet?
well, that's an actual airplane ride, but this is like the thing where they just spin you around to make you. You know, this thing's just going around in a circle. And let's imagine again that we have a coordinate system that's fixed and it's just following this person around. So this is the coordinate system. And so the camera is just always looking at the person. And say there are force sensors in the chair. Well, as this gets faster and faster, the net force measured in the chair gets bigger and bigger. That's a centripetal force. But what does the motion look like according to the coordinate system? Again, it's just fixed on the person. So it sees this person's face becoming, misshapen and like the person's turning red and then passing out and then breathing stops and whatever. And the camera doesn't understand why, The camera's just like, he's not going anywhere, So the acceleration is 0. And so again, if you plug these into, we have a non-zero force, we have zero acceleration, and so Newton's second law doesn't hold. So that's why Newton's second law, you can only apply it in the case of an inertial coordinate system. And when we have cases where the origin is accelerating or the axes are rotating, we're going to have to do a correction procedure in order to make these laws of physics hold. Okay, so next time I'll talk about free body diagrams, and I'll talk about the 3 types of forces that we'll deal with known directions, and then we'll be able to do calculations. Okay, that's all. Hi, I'm done.
I tried to do it, and I tried to do it,